We'll see this design a little bit further on with the DS1J heater. This is a box heater with horizontal tubes. We'll have a pop quiz on this later, of course. Very detailed. Again, this is a restatement of the various types. We'll skip that for now. And this talks about the heaters. Let's jump through to the fabrication process of the DS1J heater. I think we need to move along. So we're talking, let's talk about natural draft first. Basically, the draft inside the heater is, if we have natural draft heater, the stack draft is basically what is pulling the air in through the heater. There is some motive force given by the burners, which act like an eductor. So the fuel gas at pressure will motivate the air coming into the combustion area. Again, we have an induced draft fired heater. This obviously needs a little bit of work because I'm trying to remember the details on that. So let's move on. I can show you some more. Forced draft unit. In this case, we will use a combustion air blower, forced draft fan, to bring air into the burner. However, the pressure drop across the burner is such that the combustion chamber can still operate very close to ambient. Actually, in some cases it can be slightly above ambient, but generally it's below ambient. So most of the pressure drop has occurred across the burner. I would appreciate an input if some of you might have some comments. We've worked on this a little bit, but obviously it needs to be, I think we need to put this into bulleted items. It would be a little bit easier to follow rather than reading the slide and me trying to narrate it. So this is kind of work in progress. Balanced draft. There's a picture of this toward the end where we actually have a forced draft and induced draft fan. This is used a lot of times where you have a heat recovery coil in the stack to preheat the combustion air. This is an attempt to improve the efficiency of the burner, or of the overall performance of the heater. This is a picture of a balanced draft unit. This is where you're tapping off for your hot stack gas. You're bringing it down through a heat recovery coil, bringing it through a forced draft fan back into the heater. Again, those are methods for optimizing the overall performance of the heater. The intent of this is to reduce the amount of fuel gas that you have to fire, because whatever is going up the stack is basically lost to the atmosphere. So the more heat you can recover from the stack, the more efficient the unit is. The one drawback with these is that your stack temperature is limited to your gas dew point of about 300 degrees Fahrenheit. So you do not want to cool it down below that. Otherwise, as the flue gas rises, it may condense, and you could have acid gas forming inside the stack to cause accelerated corrosion. The elected to change this. We previously had slides which were not readable. They were extracts from a previous job. Rather than do that, if you look in your handout, there's a very good presentation on control of fired heaters. It addresses both the NFPA requirements for both forced draft and induced draft heaters. It has a very good control scheme shown. So if anybody here is from instrumentation, this is a very good guide for how to set up the heater controls. So for your reference, this will be put on a access on the iDrive for your future access. Also, while we're talking about the iDrive, if you'll take a look in your handout, there's a couple of references I made. There's an online heat transfer handbook, which is very good, from MIT. On the back page, you'll see a website link to that. It's a very nice reference document for you. Also, Wolverine, who makes fin tubes, they typically make a low fin tube for refrigeration processes, but they have a very good reference handbook in there which can be used for your reference. Another reference is the, I believe it's JHAR, is the JHAR and Associates. You'll see www.heaterdesign.com. That is a very good reference for all different types of fired heaters. So if you want to come up to speed on heaters, look at that. Again, our group is open for any questions you might have with respect to how heaters work, how we design them. If you have any questions about how they're mounted at grade or on pile caps, or what is the installation details, stop by. We'll be happy to share that with you. So basically, again, the P&IDs are shown on this handout, which I note here. That covers both the forced draft and induced draft P&ID controls. Again, this is a typical fuel gas skid that's used on a fired heater. This in turn is controlled by a burner management system device. Usually it's a PLC or a more sophisticated has a DCS interface. The sequence of startup and shutdown is controlled by an FPA. It's very strictly adhered to. In fact, on one of the recent jobs we're working on, the client has elected to go with non-programmable timers so that operators cannot defeat the purge times for heaters. Everything is by hardwired program, hardwired chips. So that is an issue regarding safety on these units. There are two separate controls, two separate fuel gas loops. There's a pilot gas loop and a main fuel gas loop. Pilot gas loop is obviously initiated first. You initiate your pilot flame, and then once that's been proven, you're allowed to open your main gas valve to a minimum stop and proceed with lighting the main flame. Once that's proved, then you're able to go through and continue ramping up the burner. On brand new heaters that have any type of an internal refractory, they have to go through a refractory cure out, which is critical. Otherwise, if you start it up too fast, the remaining water inside the refractory will start to spall, or the water vapor cannot expand fast enough to get out of the refractory block, and it will crack. So that's one reason why the cure time is critical, and that typically applies to the convection sections, which have a castable refractory. Generally, the radiant sections of a fired heater, which you'll see a little bit further on, have a ceramic fiber refractory, which can allow flue gas to get behind it. However, there is a special asphalt coating that is put on the inside, which prevents the condensing gas to attack the carbon steel. We'll see that in a little bit here. This is the fabrication of a fired heater for the drill site 1J for the North Slope application. It shows you the shell cans. This would be the radiant section. Shows how they roll it. These are spiders inside to keep it round. This is the vertical coil that will be inserted inside the radiant section. These pins on the bottom, these are guides that keep the coil aligned inside the heater. For this unit, the heater was hung from the top inside the radiant section. This is the bottom floor plate. This unit had 3 burners. These are the burner ports. Castable refractory, or actually fire brick, will be put on the floor here. These tubes are the guide sleeves for the coils. So once the coils are installed inside the heater, they will penetrate through these sleeves, and it will hold the coil alignment. This shows a top view looking into the convection section. Will basically mount on this plate, and you're looking into the radiant section down to where the burners would be. Again, this is a view from the opposite direction from the burners out. This shows the unit with the radiant section fully fabricated. It shows you the support columns that are used to support the heater on pile caps, which was the proposed method of installation at DS1J. It shows the unit on the side, again with the plates, the top convection section adapter plate mounted. The convection section will basically bolt to this flange ring. Again, another view showing the burner ports. Inside view of the radiant section showing the ceramic fiber installed. You can see the tube hangers on the top here. And this is the outlet going into the convection section. You can see this is all lined with ceramic fiber. We'll show you the convection section in a minute. Again, this is the heater in its normal operating position without the convection section installed. This is lowering the tube coils inside the radiant section. This shows, I guess the coils have been installed and they are ready to put the unit on the trailer for shipment to the North Slope.
Does the ceramic fiber insulate the heat?
Oh yes, there's very good insulation. The casing of the ceramic fiber, it's required that under worst case ambient, let's say hot day, no wind, that the surface temperature of the carbon steel on the outside be 140 degrees maximum. So you can basically touch that. But behind this, which is not shown, is the carbon steel material with an asphalt water resistant or non-permeable coating to keep the flue gas from condensing, because it will condense on there. That's another reason why the bottom of the heater has the castable refractory, so that there's enough heat on there that if the base floor will run at a high enough temperature to vaporize any condensate. Again, this shows the bottom view of the heater with the burner ports. It's interesting that there were no flanges on the bottom of the support columns here. These were welded directly down to pile caps that had a plate on them. A heater going down the road. This is one of the sections of the convection section. This is the tube plate. Tubes will basically be running back and forth, and you'll have a U-bend here where the tube comes out of this plate, turns around, and goes back into the section. Got a side plate, I believe. This shows the convection section. All the little spikes in there are castable, or anchors for the castable refractory. This shows that plate we looked at before with the holes in it. This shows the tubes going back and forth through that. They're manifolded on the outside. This is called the turnaround compartment. It looks from the picture here, they're doing a hydro test on it with these lines coming down. This is the completed convection section. This is the turnaround header boxes. These are the process coils in and out. Again, on the truck for loadout. These are the stacks. Stacking, welding. Let's see. Forget why we had this. I think this is just mainly an access panel to get into the stack because there was no other breaching or any other type of need for bringing flue gas into this. So that was just an access port. Let's go back for a minute. This is the bolting chair that is bolted to the top of the stack so that you can transfer the wind loads from the stack going down into the where it mounts to the base. This stack does not have what they call strakes, spelled S-T-R-A-K-E-S. They're a means of promoting vortex shedding. They basically break the vortex that could form, which would cause the stack to vibrate. In this case, I believe the stack was of a diameter and height that it was checked and found not to be susceptible to vibration. I take that back. This stack was in two sections. When we get further on, we'll see the stack fully assembled, and we'll see if the strikes are there. Shows the insulated stack ready on a truck to go. Shows field installation, radiant section with the convection section being assembled. Shows the bottom part of the stack being erected. It shows the stack, and then I think, okay, I believe that there were vortex strakes up here, but anyway, this shows you the fully assembled heater. We had there were platforms up here for the EPA sampling ports, so that once the heater was up and running, they can sample it to make sure that the burners were satisfying the permitted emissions levels. Okay, heat recovery steam generators and waste heat recovery. Actually, we only have a heat recovery steam generators. We do not have a current waste heat recovery photograph of a current application. You may see these at some of the local steam plants. They have a very good example of this over in Burbank, or in Glendale has a very large unit that you can see from the 5 freeway. Basically what this does is this takes heat from a turbine exhaust and will either use it or it will augment that with supplemental firing to produce a required amount of both saturated and superheated steam by means of taking the hot gas and exchanging the heat from the gas into a water coil, which basically flashes the water to steam. Heat recovery steam generators, as I say, can have a duct burner for increased steam production. or they can have, generally in most city applications, will have a CO and an NOx catalytic reduction system to minimize NOx and CO. We'll see that in a minute. It shows the various phases of the waste heat recovery unit. We have the various heat recovery coils and the various EPA catalyst beds. Here's a better picture here. Nope. Okay, this basically is an example of a fin coil that's used to enhance heat transfer. Rather than the circumferential fin that the air coolers have, these are more rugged. They're pin-type fins. They have a high heat transfer coefficient available, and they're also susceptible to, or they are also designed to survive in the hot gas environment with supplemental firing. Example of a steam drum. These are the downcomers on the sides. The risers are back in on the bottom center line of the heater. That's probably one of the risers here. This allows for natural circulation of the this will have water in it. The water will basically flow down through the downcomer, come up through the coil by natural circulation due to the boiling off of the water and the reduction in density of the boiling stream. Shows a cold casing design with the various layers of insulation to keep the external temperature at a reasonable level. If there's a duct burner, it's usually put at this point. It will basically augment the waste heat recovery gas to maximize the steam production. Shows you an example of a duct burner. You'll have each of these. You'll have a continuous flame off of each of these rails or grids, as they call them. Show you some piping going to these supplemental burners, fairly large size. Example of a combustion process through one of the viewports. The main issue with these is you need to ensure that the flame length is less than where the tubes are, obviously, since you don't want to have direct flame impingement, which will destroy the tubes. Example of the catalyst: you have your ammonia grid, your CO catalyst, the ammonia grid for NOx and CO reduction. And we have another catalyst back here. Pardon me. The ammonia grid is used to augment the SCR catalyst to promote the conversion of the NOx to reduce the NOx levels. Another example of just an ammonia dilution skid. This has to be brought up to one of the big issues on SCRs is you need to have uniform flow into the grid. In some cases, they will use CFD modeling depending on the hot gas path flowing into the grid. This is sometimes modeled to ensure uniform distribution. Otherwise, if you have too much ammonia going into one area, you might have ammonia drift, which will then cause more problems downstream. So that is a design issue that has to be considered. Again, more ammonia metering. This is typically ammonia block. Can't see the time here anyway. Shows installation of the ammonia grids, or pardon me, the catalyst blocks. Okay, last subject, flares. Looks like we might be done a little bit earlier tonight because I'm just about out of it here. Flares, they're very critical. They are used, basically, it's a system safety device, a process safety device in case you have to de-inventory a plant quickly. This is the most common accepted means to do that. The reference for the design is API 521. This is probably the principal equation in API 521 for flare radiation. D is the distance from the flame source. Tau, the T-value or tau, that reflects the attenuation of the flame due to either water vapor, CO2, whatever's in the air. F is the fraction of heat radiated from a combustion process. For heavy hydrocarbons, that can be on the order of 0.2 to 0.3. For light fuel gases, 20 molecular weight in that area. Measurements have found that can be used like 0.08 to 0.1 flame fraction. The Q value, which is used. Let me back up. The flame fraction is a multiplier on the Q value, so it basically reduces the amount of radiant energy that is given off by a combustion process. So if you have 20,000 BTU per pound of a fuel gas, and you have X number of pounds of fuel, that defines a gross combustion heat release. So if you have a light hydrocarbon, 20 molecular weight or less, and your factor is 0.1, so that would say that only 10% of that flame is converted into radiant energy, which is then distributed out as a big sphere over its within that region. The design, basically, the K value is a value that you would input if current practice is to use 500 BTU per hour per square foot as a thermal flux from a radiant flame. API says that you are able to survive in that environment with with reasonable clothing, and that K value would also include solar radiation. So if you're in a hot environment like Saudi Arabia, which has a solar radiant flux of about 300, that says you would only be able to have an additional 200 BTU per hour per square foot from the radiant flame. So you would basically, for a Saudi application, you would take 200, and that would be the value that you would put into the K here, and you tau, F, Q, and all the other parameters. So that would tell you how far away you have to be from that flame in order to satisfy a 200 BTU per hour per square foot flux from that. For North Slope applications, since the sun is so far away, we basically ignore thermal radiation. We ignore solar radiation, and that allows us to get a little bit closer to the flame. API addresses shows you a flame length. It also shows you the option to go higher. That distance is from the flame. You can have the distance from the center point of the flame, or you can have an integrated distance of the flame divided into 10 points, so that each point in the flame is radiating back at a different level. The cumulative effect is also considered by API. So what that means is on some flares, as you go up in elevation, you can use the hypotenuse of a triangle to either each of the 10 points in the flame or to the central point of the flame, and that defines your distance from where you have to be to satisfy the maximum K value that you've specified. So let's go on here. This is an example of it's a 125-foot elevated flare at